So let's dive into our 12 steps, starting with step 0. Should we even be using machine learning? And to think about this, we need to be fully aware of what machine learning is about, which is label all the things. So we are doing this in order to label things. If we cannot even think of what things need labeling, we're going to have a problem. So you need to think about which things you need labeled. That is your first step. So what I never want to see is we're going to use machine learning and let's find some place where we can shove machine learning because we have the goals of using machine learning. Don't start there. Instead, think about what it would be nice to have automatically labeled. And then maybe machine learning is the thing for you, maybe it isn't. So articulate the decisions that you want coming out of the system when it is fully operational. And you don't need to have any kind of specialized experience to do this. Just imagine it's already functional and it's outputting some labels. What are these labels? Are they labels like cat, not cat, or is the wine good or not? Or maybe a dosage in milligrams, an amount in dollars? What group does this thing belong to? So the sort of label that you want is going to determine what kind of machine learning system you're looking for. So let's learn about some machine learning jargon to do with labels. First off, if we are looking at binary or multi-class labels, things like cat, not cat, or cat, dog, bear, giraffe, elephant, etc., then we call that a classification task. If the label is a number, we refer to that as a prediction task or a regression task. Now, I'm saddened by the use of this jargon of regression because that means all kinds of other things in all kinds of disciplines, and especially in statistics, which is far too close for comfort. Regression refers to a certain kind of algorithm that has to do with putting lines through stuff. So I prefer to say prediction. In fact, prediction for all of it is fine, but just to introduce you to standard jargon so you don't get confused, this tends to be the first few minutes of every machine learning course. Let's just orient ourselves. Classification if there's categories coming out, and prediction or regression if the label is a number. Then you want to think about your learning type. These are 4 classic learning types. It's not all of them. Let's take a quick look at these ones. So first off, supervised learning. And some jargon even before the jargon. When we have a data set in the typical form that we would lay it out if we flattened it, the examples that we're going to learn from are in the rows. And we call them in machine learning instances. Here we have 4 instances. For each one, we have the correct label, also known as ground truth, handy. The label is what I am going for, so you might also see that called targets. That's our correct answer. And then finally, feature. This is a bit of a head explode moment for jargon because all of you are from all kinds of different fields, and I bet you have the word feature in your field, meaning something completely different, but whatever. Machine learning helps itself to your jargon, and here a feature is something that we know about our example that we can put into the recipe to learn from. So in other disciplines you might see feature called variable or predictor or attribute. What are the features in these data that I have given you? Can anyone tell me? All I have given you is the information about what color the pixels are. Pixel this one, here's its red, green, blue. Pixel next one next to it, here's its red, green, blue, and so forth. So this is a very short, very fat matrix. 4 rows, lots and lots of columns, all about those colorings. And you're going to be my machine learning system now, and we're going to do a bit of transfer learning. If this was the only visual information you have ever received in your life, you would not be able to succeed on a matrix shaped 4 by too many. But because you already have a trained vision model in you, it only takes a small adjustment for you to be able to perform my task. So, cat, not cat, not cat, cat, and please learn to classify this one for me, please. Not cat. If you said anything other than not cat, you will fail my testing, and I'm going to go with a different system. So again, supervised learning is where, for every example I give the system, I have the correct answer handy. Now, let's look at unsupervised learning. Here I have for you 6 instances, and your job is to put them into 2 groups using whatever rule you like. Just put them into 2 groups for me. Anyone? Tongue out, not tongue out. Great. So what are the labels that are going to come out of this system? Are they tongue out, not tongue out? Or am I doing some trickery? The labels that are going to come out are just like A and B, or 1 and 2. They have no human interpretable meaning. The tongue out, not tongue out is the recipe that we're going to use to separate them. The output is just like thing 1, thing 2. And so, all right, 1, 1, 1, 1, 2, 1 is what's going to come out, 2 groups. Some other way to separate them. Sitting, standing, okay. So 1 or 2? You're responsible for this, so you tell me. 1, okay, how about this one? 1, how about this one? 2, this one. 2, this one. 2, this one. 2, see? Easy. Any others? Cat selfie, not cat selfie, I love this one. All right, so, what do I hear? 1, 1, 1, 2, 2, 2. Okay, so this happens every time with every audience. You ended up separating these things. I didn't make it sound like there were right answers and wrong answers, but you know, I'm still deeply disappointed in you because here you are saying tongue out, not tongue out, cat selfie, not cat selfie. When I, as the proud mother of these 2 individual cats, really hoped that what you would tell me is here is cat 1 and here is cat 2. But instead, look at you with your sitting, standing, and all the rest of it. And every other audience does this as well. Actually, one audience came really close to separating them, said ugly cat, pretty cat, and I was like, whoa, 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 we're going to have to talk about this later. So here is Huxley, and here is Tez, 2 individual cats. Now look, if we had done supervised learning, and I had given you a few examples of Huxley and a few examples of Tez, of course you would then go and label things that way. But I didn't tell you what I was looking for. I just said, here, take all this stuff and split it into different groups however you like, or by whatever the rule is that is part of your internal algorithm. Now, that's the thing with unsupervised learning. If I don't tell you what I want from you, I just tell you to put things into groups, I get what I get and I don't get upset, right? It's no guarantee that the system is going to come up with what is actually dear to your heart in this example. Just splits things into different groups. And so what you will do with unsupervised learning is you will look at the results and you'll ask yourself, is this something I can use for anything? And if not, kick the system and ask it to split them some other way and keep doing that, and maybe nothing dear to your heart ever comes out. It's just separating them into groups. Now there's another little cautionary tale here. See, if you are like me, these cats, they're where your heart's at. And whenever you look at photos to do with them, you see individual 1 and individual 2. And you expect the machine learning system to be looking for that because it's precious for you. And then, let's suppose the system does give you these splits. 1, 1, 1, 2, 2, 2. The human foible here is to think, look, machine learning is separating Huxley from Tesla. You'd think, right? Except maybe turns out that what it's doing is asking radiator, not radiator. And all the photographs that we took of the first cat didn't have radiator, and all the ones that we took of the second cat did. Or maybe the first set of photographs was all taken on a sunny day, and the second set was all taken on a cloudy day. Well, how do you know that this rule has any human interpretation? At this point, you don't, and you shouldn't, and you should stay cautious. If you want to ask whether there is that story in these photographs, you need to make sure that you design an exam for this system with new data, where if the system passes that exam, the only interpretation can be that the story is true. So the exam had better have cats taken on the same weather conditions across a variety of locations in the apartment, and then if it still separates them in this way, then you have a bit of evidence to start talking about perhaps it is finding Huxley and Tesla. Don't trust that because this is what's dear to you, it is also doing this. And the other little cautionary lesson that we get here is you, humans, you're a pretty good algorithm for this. I want you to remember that you didn't find what I cared about. You didn't pull out the two cats. So a data scientist going about applied machine learning, expecting that the algorithm is going to give them what they care about, well, they are possibly in for some disappointment. And don't think things like machine learning is better than humans, so it can do things humans can't, so I expect it to work here where humans will fail. Don't expect the reverse either. Oh, humans are so good at all these tasks, they're going to get everything I care about. In fact, this whole testing thing, it holds not only for machine learning, it also holds for stories that humans come up with based on data. When you look at some data and you form some opinion, if you want to be able to take that opinion seriously, design an exam, and check that that little recipe that is your opinion actually works on the new situation also. So unsupervised learning is the search for patterns. This is where you don't have any labels, and some keywords here are data mining or clustering. Then, semi-supervised learning, exactly what it sounds like. This is where some of your data are labeled and some are not. So imagine that you're really excited to build yourself a cat-no-cat classifier. And of course, for that you need data, so you download 1 million images, you grab your 6-pack of Red Bull because you want to do supervised learning, and you start labeling them as cat, not cat. Cat, not cat, not cat, cat, not cat. And by the time that you are about halfway through, exactly. Curiouser and curiouser. And then it's 3 a.m., and you have labeled 300,000 images, and you can stand no more photographs, and there's 700,000 to go. What can you do? Well, the first option is the most pragmatic. Remember, our goal is to make it work. Let's see if we can get a recipe that actually works. So why don't you just try it with the 300,000 first and see if you can get success there? No one said you had to label all 1 million of them. See if 300,000 can be made to work. So for now, throw away those 700,000 and see what you can do with what you got. If that is not good enough for you, then you don't have to go straight for labeling all the others. You might be able to squeeze some goodness out of the unlabeled photographs. I hope your intuition already tells you that the unlabeled ones are worse as data than the labeled ones. Makes sense. But they're better than nothing. And so by combining the two techniques, essentially, you might be able to do better without having to label everything. And that is the nature of semi-supervised learning. So you do that if you couldn't get supervised learning to work. I want to point out that we are never here by choice. We're here because time is limited or budget is limited, and we want everything labeled because supervised learning is the easiest learning type. If you can frame your problem in terms of it, do it. Sometimes we just don't have the luxury of everything labeled, so we're forced to rely on these other complicated techniques. So this is a blend of the previous two, where you've only got some of the correct labels. Then, finally, reinforcement learning. So in our Atari slider game, when we ask the thing to optimize its score velocity, we're giving it a little bit of reinforcement, some reward or punishment signal, but what are we actually asking it to learn? What are the labels that we are getting as output?
Score.
If it's trying to output the score, why not just set the score to infinity and call it done? It's not trying to output the score. It's trying to output the movement. But it's not just working with one movement. It's dealing with whole sequences of movements. The thing that really separates it from supervised learning is that there isn't immediate feedback for every individual move. When we move our little paddle left, for that move, we don't get immediate feedback. We don't know if that move is the one that's going to be responsible for us dropping off the screen later. There's some element of delayed feedback, and you're dealing with whole sequences of stuff. And you need to go to reinforcement learning, and that is, I'm sorry to say, harder than supervised learning. So you can diagnose your task. If you're dealing with sequences of actions, there's some notion of reward or punishment, there's some notion of score, there's delayed feedback, so you don't get an immediate signal for the total goodness of every little movement, and the system influences its environment and input. So there's that last bit. The actions that the system takes also influences the data that it will be seeing coming in. So if you have all these, you have reinforcement learning. Reinforcement learning today is hard. You are going to have to be buddies with the researchers, and if you read research blogs, they'll tell you the gory truth of what's actually involved here, which is a lot of failure. And they will, there's a blog I love by a Googler on this topic where he describes just, it's best to just think of this as a demon that hates you. and then you'll feel better about it. It's beautiful when it works, most of the time it doesn't. So we'll focus on supervised learning for the rest of this course, but now at least you know how to diagnose whether you have this one. Just very researchy today. Okay, so if you cannot even imagine what sort of decisions or labels you want, please stop. Machine learning is not for you, not yet. Maybe you want some other area in data science, like data mining or descriptive analytics. Actually, let's talk about what is data science even. I think of data science as the discipline of making data useful, and within that discipline, you have statistical inference, you have data mining or descriptive analytics, you have machine learning, all under that umbrella. How do you figure out which one is which? I mean, some people will joke that machine learning is just statistics on a Mac and stuff like that. I quite disagree with that. Let's see if we can figure out a taxonomy. So one proposal, I hope you're enraged, I am, is based on the tooling. No. You can, with some creativity, use all of them for all of them, especially since we at Google are doing things like making BigQuery able to do ML for you. So now you can have machine learning right in SQL, so that's just confusing if you try to do it based on tooling. So instead, how about not that? How about the algorithms and math stuff? Actually, a good data scientist with cunning and the right level of stubborn perversity can use any algorithm for any of these things. It's not the algorithm that determines which is which. So instead, I propose this separation. None, many, few. Any guesses what none, many, few refers to? Data points? Whoa, hang on. How do we describe when you don't have any data? I think we'll have a problem. The number of decisions, exactly. Here in data mining and descriptive analytics, we are not making any decisions. We are simply trying to get inspired from data. We're having a look at what is here. We're learning what is here, and we're not taking it too seriously. We're not learning anything beyond what is here in our data. In machine learning, we are going beyond our data in the sense that we are trying to make a recipe that's supposed to work on new stuff beyond the data that we have on hand. And statistical inference, statistics for short, is for making one or a few careful, important decisions where we don't have the correct answers until we've made the decision, and then the universe punishes us or doesn't. So we are carefully working with making a few important decisions. And the whole discipline together, data science, you can think of that as the discipline of making our data useful. Let's have a flowchart to diagnose which one we're dealing with. So our first question should always be, are we making decisions? And if the answer is no, descriptive analytics, data mining, that's the one for you. And if you want those fancy algorithms, you can use machine learning algorithms for descriptive analytics. You can use statsy stuff like t-tests for descriptive analytics. It's just the way that you use them is very different. You don't worry about the philosophy behind it. You don't worry about whether it's right or wrong. You quickly apply a whole lot of different algorithms, and you see if anything seems to inspire you. And whatever inspiration you get, you just interpret that as, when this math is applied to these data, the combination together gives me this result. What does it mean? Nothing yet. So if I'm going to go for meaning beyond the data, then I have to look at one of the other two areas. So descriptive analytics in some sense is like a printer. Let's take this image and see what is here. It starts out as a thing on an SD card that we can't make any sense of, so we can't get inspired from it. Well, let's look at it and see if there's any inspiration. And just like with photographs, you should know that if you are walking down the street and you stumble upon some image lying on the pavement, you shouldn't pick that up and learn all kinds of marvelous things beyond that photograph. Data science is essentially Photoshop. You can do benign things with Photoshop, like have a look at what is here. You can also slice it and dice it and make it tell any story you want. So if you want to use that photograph for decision-making beyond what's in the image, you need to be in control of how that image was taken, and you need to be in control of what has to be in that photograph in the first place to sway your opinion. If you just found some data lying around and you looked at it, please don't take it too seriously. All it says is, this is what happens to be in this particular image as it is sitting in front of me. And that could be inspiring. Just don't learn more from it than you should. Next question. If we are making decisions, can we just look up the answer? So maybe our decision is directly based on last year's revenue figure. Let's look up last year's revenue figure, and off we go. Well, back to descriptive analytics. Just look up the answer. You're dealing with facts. But if you can't look up the answer because all the data you care about isn't available to you, like you care about tomorrow's data, and you only have today's data, well, then you have to deal with one of the others. So then the next question is, how many decisions? And if your answer here is many, machine learning is what you want. And that is where we build a recipe out of today's photos, out of this pile of photos, that we might use for determining whether we have a truck in a photo we take tomorrow. We're making a recipe out of our old data to succeed in new situations. If the answer is few, next question is, are we scared? Is the decision important? Because if the decision's like, hey, based on what's going on in fashion today, should I buy a blue t-shirt or a white t-shirt? Please don't waste your PhD statistician's time on this. Get inspired and go buy your t-shirt. It's only when the decision is important, when it matters, when you want to make it carefully, rigorously, in a risk-controlled manner, that you want statistical inference. And in order to purchase that rigor and careful control, all the conditions need to be carefully put in place. You don't get those guarantees just by sort of math on some bad data and off we go. Everything has to be done carefully, especially the framing of the conditions at the beginning, which the decision maker makes. So what's a really careful risk-controlled decision that we might want to make? Should we launch this machine learning system we've built? This is a system that's important. If it doesn't operate correctly, we'll lose all our users. Should we release it? Yes, no. That seems like a pretty important decision that we might want to verify with statistical inference. So I kind of think of machine learning as make it work, and statistics as now that you think it works, does it? It's about coming to conclusions beyond our data safely. And yeah, don't forget data. As part of step 0, we're still talking about step 0, machine learning just simply does not work without data. And this should seem obvious now that I've talked on and on about how this is expressing yourself with data, with examples. And yet I still end up in these consultation situations where people ask me, like, if the thing can know that this one is from Canada when I have never given it any information about Canada. You're like, well, if there's nothing to learn from, and if you have no examples of what's relevant, then how are you possibly going to make up the idea of Canada out of nowhere? You can't do that. And then, even worse on that one, I was like, so what are these objects that you have information about that you're trying to predict what country they're from? They're like, we actually don't have data on them either. We just have the country names. I hope that you won't be in the situation of trying to proceed too far with that with a straight face, right? You will see why that's a problem. You need the ingredients to learn from, otherwise there's nothing to base your recipe on. At best, it will just be predict the most common country in the set, like we did with our regression example. We just use the average calories every time. Same here, it'll just give you most of them are from this country, just keep repeating that. And if it's never seen Canada, it's not going to make Canada up for you. You need the data to learn from. So if you know you don't have access to data, or you don't have access to the hardware that's going to move the data around, fix that first before you go to machine learning. Alrighty, step 1, set your objective. And I hope you've been noticing that the team members change in each of these chapters. So here our main players are our decision maker and our domain expert. Now, setting an objective can be nuanced. Which of these is the good behavior? Oh, come on, which one is it? The one I'm looking for is it depends. What does it depends on? On the owner, the decision maker. What were you trying to get out of your dog? Do you want a sheepdog or a police dog? Because if you wanted a sheepdog, this is probably not the good behavior. Now, when should you be answering this question if you are the dog owner? Yeah, before the training, when the dog is a puppy, maybe even before you got the puppy, you should say, aha, what I'm going for here is a police dog. And yet, for some reason, teams will try to do this much later in the project, after algorithms have been done on some data for no particular reason. Now that is just like putting the poor dog in the basement with food and water, leaving it for 5 years, and then opening up and saying, so how's my sheepdog coming? It is not going to work. Now, you don't need to know how the dog's brain works in order to start training it towards being a sheepdog. You don't even need to know exactly how to do that training to start answering this. The first goal is to say, well, what's the goal? Now that we know we want a sheepdog, once we've made that decision, we can start looking into how to get the sheepdog. The first question is, what are we actually trying to do here? And it's amazing how often this is not the first step when people try to apply machine learning. Things crash and burn when you skip this. So let's do a quick example, learn some basics with cat classification. So we're going to build a cat classifier, and we have a little guide here. This is a pen and paper step. You can do most of this step 1 thing with pen and paper. You don't need special expertise. You don't need to be a mathematician or a programmer. Anyone with common sense can do this. So what's thing 1? Write down the outputs or labels for our cat classifier. May I have some suggestions from the audience? What should it output? Cat, not cat. Very nice. Couldn't have said it better myself. Fine, what's next? Consider mistakes. What mistakes can it make? Now, this is a very simple setting, so there's only two things that can be true. Cat, so you can see him in there, or not cat. And over here, the machine learning system only has those options. So if there's a match, we call that a true something. If there's a mismatch, the system's being false with us. We have built the system to be very excited about cats. And so when it thinks it sees a cat, it goes positive, positive, I got you a cat. Which is why we'll call that a positive event, and no cat, well, negative event. Now, of course, sometimes it goes, I got you a cat, and it's just seeing things. Mistakes are possible. So putting that together, we get the standard jargon in classification, the event names here. Next, assign project scoring. Figure out how to score many, many decision outputs and expect that this system will make mistakes. So imagine it has made some mistakes. Which mistakes are worse than which other mistakes? And this is about lots of outcomes. You're not going to use machine learning to just make 10 decisions for you. We're talking hundreds, thousands, millions, billions, that sort of scale. So it's going to have made lots of decisions. How would you score different combinations of those outcomes? How were you going to think about this? Well, first off, how about you use a little brainstorming tool? Why don't you imagine that 100 such decisions have been made, and there's some of every kind of good and bad outcome, and you tally up the counts out of 100 of each possible outcome. You just make some numbers up in here that should sum to 100. Are you confused? If you're confused, good job, you have named this thing. Its name is a confusion matrix. And a confusion matrix simply shows you exactly that, the outcome counts, all the total number of times that each situation has happened. And you're going to use this for brainstorming. Confusion matrix, what a cool name. And then you realize it's just this? Like, seriously? Just a 2x2 table of what happened versus what should have happened? And then you realize that this is all of machine learning. The names are just so fancy. And then when you look at what's under the hood, you're like, are you kidding me? I was intimidated for years by this. And it's also quite funny, some things have been named both by statisticians who love the thing to just be called exactly what it does on the tin, and by machine learning folk who love the real fanciness. And you can kind of even tell who did the naming, just from the name. Confusion matrix, neural network, artificial intelligence. Maximal margin classifier. Anyway, yeah, actually, if statisticians had named machine learning, we probably would just have named it thing labeling with examples. And can you imagine the industry getting all excited about, like, today the new hot thing in the industry is thing labeling with examples. Let's all go to a conference on thing labeling with examples. It's sold out in 11 minutes. Machine learning. Anyways, grumpy statistician right here. So what's the score? Well, the score is up to the decision maker, and there's lots of options. It comes down to what is important to the business. The decision maker chooses this. This whole thing, decision maker, see it as a board game that you are making. How do you want to score better players versus worse players in your board game, the solve this problem board game? Which outcomes are worse than which other outcomes? That's up to you. And let no nerd ever bully you on this. Because the machine learning research folk, they work on building the algorithms, and there's certain things to do with the algorithms that make them like various scoring functions. We'll talk about that shortly. It doesn't matter what scoring functions they like. What matters is what is important to your business. And that is how you should evaluate the performance of your system. How well does it deliver on what you have asked for? So please ignore all that stuff. It might come at you, and I'll explain to you why it might come at you. And seriously, just go with your heart. How do I want to score this? And remember how important it is to pick a metric carefully. We looked at that parking lot example. Picking a bad metric can tank your business, or worse. So they were going to ask about the various types of mistakes, and they're just going to see which one should get a worse score than which other one. So they're going to imagine that 100 photographs were classified, there were some mistakes. What's worse, this situation where we made up a bunch of cats but we didn't miss so many, or this situation where it's reversed? How differently do you want to score these things? And by searching your soul a whole lot, you come up with a scoring function which we'll call the business performance metric. So let's create that performance metric. And there are a lot of options here. Not only these, many more, but here are some classic ones. So let's learn these classics. So accuracy, precision, and recall are the ones that you'll find in many 101 courses. Let's look at them. But before we do that, I need you to help me classify these images as cat, not cat. So everybody shout, just to wake yourselves up. Cat, not cat. 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 Not cat. Cat. Not cat. Not cat. Come again? Big cat is not an allowable option. We said at the beginning, that's why we did this at the beginning, cat or not cat. Big cat and maybe cat aren't allowed. You see now why the decision maker is so important. The right answer here depends on why this system exists and what we're trying to achieve with it. And I guess I'd better fill those big shoes for the purpose of our example. So I'm going to tell you that the system exists as a pet recommender. And whenever it says cat, it should be saying cat about something that's from the cat family, which in its standard adult form is safe to cuddle. Not cat. If you're still saying cat, take out more life insurance. Okay, and then we imagine machine learning has a go. Oh dear. Thanks, machine learning. So this is where it says not cat, that's where it says cat. Let's compute accuracy. That's simply how many did we get right. So we got 3 right out of 8. There's our accuracy. Let's practice saying these labels out loud. This one is true positive. How about that one? Allow me to show you how to speed yourselves up. Don't try to say it in one hop. True positive, false positive, whatever. Instead, did it think we got a cat? Did it get it right or not? Let's start with the second one. Did it get it right or not? That's false. Did it think it found a cat? That's positive. False positive. False positive. True negative. Say, don't think of them together. True. Not cat. Negative. False negative. There you go. And so when you are fluently showing off that you are totally cool with this whole classification conversation that's going on in the meeting, you'll use the separate them in your mind first thing to ramp up your fluency. Okay, let's look at the other metrics. First, precision. Precision is the fraction of actual cats among the cats that the system found. So in order to do that, in order to compute that metric, let us ignore all the things it didn't find as cats. Boom, gone. This is our denominator. All the ones it presented to us as cats. Of them, how many were actually cats? 2, giving us a precision of 2 out of 5, 40%. Recall has the same numerator, different denominator. Recall says, of the things that were there that were actually cats, how many of them did it return for us? In order to compute it, we need to know what was actually a cat here. And that's those 4. And of them, how many did it give us back correctly? 2 out of 4, giving us a recall of 50%. So different metric. Now, whether you'll be in more of a precision mindset or more of a recall mindset depends on your application. So let's brainstorm. You're going to tell me more precision or more recall for these two examples. So for the first example, you are busy people, yes, everybody? And you read, everybody literate, yeah? Okay. I posit that there are more books in existence that you will enjoy than you could read in all the spare time that you have. Yes? Happy? Okay. So you want to build a book recommender that is going to suggest to you what to read. Suggest to you that you like it, don't like it labeling for books. Will you be in more of a precision mindset or a recall mindset? What do you say? I'm hearing precision, and that is correct. If you want a recall mindset, you're saying, I need an exhaustive list of every book that I could possibly like, and I'm willing to accept duds also. Now, who's got the time for that? Come on. Precision is a way of saying, hey thing, don't waste my time. Leave things out. Leave out books that I would like. But what you return for me, let that actually be good. That's what precision is saying. Hey, let's try another example. When we're not reading books, what's our other favorite weekend activity? Robbing houses of jewelry. Now, when you are robbing a house and you have a big bag, are you in a recall or precision mindset? If you're saying precision, you are going into that house with your jeweler's magnifying glass, and you are checking every item. Is it valuable or not? Because you'd better not get any costume jewelry in your bag. Is that how we rob houses? No, you're flinging everything in there because you don't mind getting the duds in your bag. You want to make sure you don't miss out on the diamonds. You want to make sure that of everything that was valuable in this house, you got all of that. And if some plastic comes along for the ride, you're cool with that. That is recall. And so, again, depends very much on your application which one you want to go for. To summarize, a system with high precision is going to leave good things out. But what it returns is of high quality. A system with high recall is going to give you a lot of duds, a lot of plastic jewelry, but it returns most of the good items that were there all along. And you don't have to go for one or the other, or even accuracy, which is all mistakes are equally bad. Hey, there's all kinds of crazy blends you can go for. There's something called an F measure, if you've heard of that. That's just a way of balancing precision and recall. I care about them equally, so that's the harmonic mean between them, whatevs. Figure it out. You are allowed, as business decision maker, to choose what is important to you, to your business problem. And let that be the metric you pick. What is optimize? If I talk about optimizing a function, what does that mean? Well, essentially, that is about picking the parameters or values to fill in into our recipe that do the best job of achieving what we're after, in this case, a taste score. So maybe we have many different ways that we could make soup, many different options for how much salt to put in and how much onion, etc. And so we would figure out what is the relationship between these potential values and the taste. And instead of having to individually try every combination in order, we would have an optimization algorithm tell us, boop, go for 2 teaspoons of salt because that is where you get your best value for the taste. And similarly, in this machine learning setting, there is a score that the thing is trying to optimize, and it's going to try to figure out where to set our settings so that the score is highest on the data that we learn from. And you're going to see that in action when we look at the black box section. So essentially, optimization is all about figuring out what the particulars in the recipe need to be so that our performance is as good as possible. I forgot I had this slide. So, optimization boils down to finding values in the recipe that give our best metric performance. And ideally, we would be working with the metric that the business decision maker cares about, but beggars can't be choosers. We don't feel like reinventing the wheel and rebuilding an algorithm from scratch. So we're going to take an existing one when no one asked us what metric we wanted to work with. And so we will then be optimizing some other function. All right, so what's next? It says here, think about the loss function. At a loss as to what a loss function is? Well, look. Our business decision maker just made a performance metric for scoring the system. Ideally, that is what the algorithm would use for learning how to do good behaviors. Unfortunately, that algorithm is not something that your team custom made. It's something that some researcher already made for you. It's already prepackaged, and it was made long before anyone knew what your particular business application was going to be. And inside that algorithm that you get off the shelf, in there is already a performance metric encoded. That thing is called a loss function. So that's the actual function that the algorithm is going to work with, because no one asked the business decision maker what they wanted when the algorithm was made. And it's called a loss function because machine learning folks need to rename everything. Before they came along, we used to call them objective functions. And that's because the objective could be positive or negative, but they take a very sticks are better than carrots approach. So they term the scoring of the board game in terms of errors and how much we want to penalize those errors or mistakes. Yeah, could always put a minus sign in front of it, whatever. So it's generally framed in terms of computing the badness, and the system is trying to bring the badness down. Less loss is better. So this is the function that's operating inside the system, and it is different from your business performance metric. And this is what I mentioned earlier. Don't be bullied by those researchers who tell you that your business performance metric should be a loss function. I've seen this so many times. Stat 101 says RMSE is a great choice for a regression problem, so your business performance metric should be RMSE. Your business performance metric should be whatever your business cares about. And so effectively, you will end up with two functions in operation. One that the system is going to optimize, and one that you actually care about. Now, surprise. If they're moving in opposite directions, machine learning will hurt your business, not help it. Which is why it's a good idea to think about comparing the functions. So, take your performance metric, let's say ours is accuracy, and compare it with a classic loss function, and see if they kind of align. So, a classic one you see here is called cross-entropy loss. Guess who named that? It sounds fancy, and it comes with an equation that has logs in it, oh my goodness. Or if we say it simply, are your ones near 1? That's what that function is doing. And you don't even have to read it. If you're lazy, there's an even easier way to compare it than to look at the formula of the one, look at the formula of the other, and math on them. You can simulate. Simulation's like the best thing in the world. I loved simulation before it was cool, because you needed the computing power, and really early on you'd have the lazy stat student that's like, hey, you could just simulate everything except like it takes all weekend to run, and now it takes that amount of time, and now everyone's getting on board with it. You should all simulate all the things. Okay, so let's simulate the comparison. So what are we going to do? We have implemented, we go to some package, R, Python, whatever package that calls itself cross-entropy loss, whatever, cool. And we don't even have to read the formula. We've got another one that says accuracy. We simulate a fake data set. That random, fake one. Fake outputs. Cat, not cat, cat, not cat, whatever. And then the truths. It was actually a cat, it was actually not a cat, so forth. And then we score it with this function, and we score it with accuracy. Okay, so we get a pair of scores. And then we put it as 1 point on a plot. And then we do that again, and we do that again, in a loop, lots and lots and lots of times, until we get such a thing. And now we will look at this glorious mess. We do it over different conditions, different data set sizes and so forth. We get this glorious mess, and what does this say? So, accuracy. Is accuracy better or worse as there's more accuracy? Better. More accuracy is better. So this direction is better. Okay. How about a loss function? Does that get better or worse in this direction? Better. So what are we seeing here? This one is, when this one is going better, this one is also going better. That is a wonderful thing to see. They are not countering one another. Inching towards doing better on cross-entropy is not going to shoot us in the foot for accuracy. Okay, they're not the same function, so we might take a little more time getting to where we're going, but at least we're not on a wrecking path here. Great, I can proceed. That's the kind of reasoning. Now, there's no need to commit yet. Actually, you'd be crazy to say, I'm definitely going to use the cross-entropy loss function, because you are a long way away from selecting your algorithm. That happens way later in the process. And you don't know what the actual loss function is that's going to be implemented in that algorithm. So why am I even making you do this? To make sure you're not asking for the moon, that's why. After you've developed your business performance metric, it may so happen that there is no classic standard loss function that captures the idea there, that goes along with what you are asking for. And if that's the case, machine learning is going to be really, really hard. Maybe you should back away slowly, or maybe you can go to the researchers and start talking to them about making an algorithm that is customized around what you, the business decision maker, care about. And the final thing, most important thing, is set performance criteria and commit to them. Performance criteria for both of our decisions. What's the minimum we'll accept to take this from prototype to production? This might be an important decision if that's a lot of engineering effort. And then, what is the minimum performance that I require to release it in full on all my users or customers? And you need to decide these up front. Why do we decide up front? Because we are human. And as humans, we fall in love with the things we build. As we pour our hearts into it and we put effort in, even if what we have made is a pile of poisonous rubbish, we look at it and we say, oh, but the performance is not so bad. And that's how awful things get released. And so while we are still sober, before we have fallen in love with anything, we take a good, cold, hard look and we ask, okay, what is the minimum I accept? And then we commit to crushing this thing if it doesn't make that minimum. Because we have just answered before we've poured all our love and energy into it, like, seriously, if it's less than this point, it just really shouldn't exist. It would be a bad idea to let it out there. And that's how we protect ourselves from bargaining ourselves into bad situations. Now, this is not an aspirational metric. You can have that as well. That's a guiding star thing, and that can move around all you like as you need to change it to motivate your team. But what you test against later has to be preset at this stage, and it has to be a minimum that you're going to accept. This is, as economists like to say, incentive compatible. If you use the guiding star here, then you'll test against it, and if you end up performing above that, well, you would have performed above the minimum, so same thing. But maybe you end up getting a performance that lands somewhere between your minimum and your guiding star, and the conditions of testing say, well, under that, you have to kill the system, so you miss out on a system that actually would have been viable for life. So I hope you realize why I have to laugh to myself a little bit when people ask me, hey, Cassie, is machine learning like better than human? Well, it depends on you, the decision maker, because tautologies are tautological. If you said that the thing must be better than human, and you tested it correctly, and it now exists, it is better than human. But maybe that wasn't the performance you required, because you could have made a profit on it being at scale, but a little worse than human. That's maybe still fine and profitable. And maybe you set your performance requirements at below human performance, and that's okay. Maybe it's below human performance. It depends on you. If you need it to be that good, then don't release anything that isn't. That's all there is to it. So key message here, the proof of the pudding for machine learning is always in the eating. And you have to figure out how you do the proving up front in this step. Decide on how you're going to measure success and set that cold, hard minimum early so you don't bargain yourself into releasing rubbish. Step 2, getting data. So this is where the data engineer works with the domain expert and gets data. Now, I realized at some point, to my horror, that people had this funny idea about how machine learning systems find and ingest data. Approximately this. The system sits, according to popular belief, sits on top of the business somewhere, floats around, and then goes and finds data, which it gobbles up, and when it's done with that, it goes and finds by itself, runs about finding data. This is not how it works. Instead, it is the careful effort of the engineers that feeds the data into the system, and it will not look at anything that you do not tell it to look at. So it won't go and figure out all by itself that it has to go and look at those examples and not those, or these features and not these other ones. That is up to the engineers to figure out. And so you need to think about which data sets, which ingredients would you like to feed into it, and then you need to go and write all the code, especially if it's at scale, to deliver that. That can take a long time. Then in step 3, you are going to split your data. This is the step in which I'm going to introduce a really important concept. We are going to give a name to the scariest nightmare in machine learning. And I'm going to, hopefully, if I do my job right, have you want to split data at a sort of visceral, emotional level. The idea that someone might not split data would disgust you. That's what I'm going for. So let's see if I manage it. Here we have a deterministic application. We have a feature here on the x-axis, 0 to 100, and our job is to use the feature to predict the ground truth, 0 to 200 over there. Can we do it? Can we find a recipe that takes us from the feature to the ground truth? It is so difficult, it is so hidden, that recipe is so hidden, it's in fact hidden over there. All we got to do is take the feature, double it, and add 5, and we're good to go. And as long as we do that, there'll be no mistakes. That is way too easy, come now. Why don't we put in some noise? Noise that you will not be able to ever predict with any information available to you. Boom, random. 200 data points that are based on our line plus some random noise. There we go. Now that we have noise, does that mean that we are stuck, that we should just guess entirely at random, haphazardly? Or can we actually do better than guessing at random? I think we can do better. Let's use machine learning to do better. Let's predict our ground truth, our label, our target. And let's use this objective function, this performance metric, which is called RMSE, or root mean squared error. That one is probably named by statisticians because it is named for the recipe that you use to calculate it backwards. First you compute each error, then you square each error, then you take the average of all those squared errors, and then you take the square root. Boom, that's the score for the whole thing. Nice. Or another way of thinking of RMSE is simply that. Stupid model, be less incorrect. That's what we're going for. So we do better when RMSE goes up or down. Better is less of it, less error. And what's the best possible RMSE? 0, no errors at all. Fantastic. So we are going for be less incorrect. And let's look at half of our data. So I've split it into 2 pieces. I've taken the 200, I've taken only the first 100, and we're now going to learn from this. We're going to make some recipes. So the first recipe we're going to try is to use the model that we saw before, the true one. We're cheating a little bit. We know what the right answer is. Let's see how the right answer model does here. And it gives us an RMSE of 22.24. because there's errors. It's not perfect. There's noise. Okay. But maybe we hadn't seen all the behind-the-scenes setup here, and we didn't know what the conditions of this universe were. Maybe we were just a data scientist with this information arriving to us, that's all we got. And we're told that our job is to fit a great model that makes as few mistakes as possible. And so we start to do a thing, and you'll totally recognize this thing. You've done it yourselves in science, you've seen your science colleagues do it, it's amazing. So here we go. So you start looking at this plot, yeah, analytics. And then you see it. And when you see it, you can't unsee it. There is a wiggle here. Yeah? Do you see the wiggle? It's totally a wiggle. Come on. The data have a wiggle. This is absolutely a system. And you know what? The science says that wiggles make sense here. So let's attempt a wiggle model. Okay, there we go. Now, do you expect that the performance is better, lower? RMSE is lower when it's better than before? Or do you expect that things are worse, so this number has increased? Better or worse? What do you think? Better. Better, by definition better, because we are closer to our data points now, and the errors are the distance of the points to the thing, and that distance has been shortened by us contorting a thing through it, so of course better. You know what, while we're on this reasoning track, why not just take things to their logical conclusion? What's the RMSE here? 0. The very best is best. I take my bow. You look disgusted. But maybe you don't yet have the vocabulary to express what it is about this that offends you so much. So let me see if I can fix that. Remember, we have one job: to do well on stuff we haven't seen yet. Not to memorize our old stuff. To memorize our old stuff, that was a perfect solution. But we want a system that can do well on new things, so can this one actually do well on new things? Well, why don't we find out by looking at how it does on new things? So here's the other 100 instances. Let's see the performance. First, the model that entirely consists of signal and no noise, the true model, if you will. Above, in blue, will be the previous data's performance for that model, and this new 100 instances on the same model below in red. About 22 for both of them. Pretty similar, and that's what we should expect. Now, when we look at wiggle, so remember this is 22 as far as you're concerned, let's see what happens with the numbers. Higher is worse, lower is better. This one, what do you think will happen? You saw it already. Down, better. How about that one? That's reading more like 23 now. More badness. Uh-oh. That looks like an uh-oh. Again, let's go to our logical conclusion and see if it feels like an uh-oh. 0 versus uh-oh. This situation is called overfitting. And for the last time in your lives, you get a free pass not to feel emotion when you hear this word. From now on, and I will quiz you after lunch, when you see or hear this word, you will feel horror, terror. This is your worst nightmare. This is the profanity in machine learning. Overfitting is what you spit at your enemies. You have one job. Make it work on new stuff. And instead, when you have overfitting, what happens is, there you are, memorizing your old stuff, learning all about the noise and irrelevant stuff in your old data. And when you release your system to go operate on new data, it crashes and burns horribly. And you ask yourself, why did I even get out of bed this morning? It would have been better if I hadn't data scienced. That is overfitting. And we're going to try really hard to avoid it. So overfitting is our worst nightmare in machine learning. It happens when our model is just the noise, the peculiarities of the old stuff, and has nothing to do with the general reality of the new situations. And you need to realize that any fool can get excellent results in the data where they build their models. As proof of that, I need only remind you that even toddlers can play that game where you connect all the dots. The real test is, does it work outside of where you got to cherry pick and torture those solutions? And actually, you should apply this thinking to every endeavor, not just machine learning. When you look at academic results, what scientists publish, it's very easy to make a compelling story pop up out of the data set you use to make that story. Ask, does the story still hold up if you go and collect a bunch of new data and then test the story? In the old data, it's just an opinion. If you want to see if the opinion holds any water, go to new data, test it properly. You can contort some beast of an understanding, both as a human and as an algorithm, in whatever data set you use to do that process. Might have nothing to do with reality, though. Just because it involved data and math doesn't mean it creates truth. Even toddlers can play that dot-to-dot connecting game, right? You can always connect your dots. And you can even connect your dots without realizing it by using a system that's complex, like neural networks. So you have one job. Optimizing for fit on fresh data. And if you don't do that, you may as well not have a machine learning system. And for that reason, you need fresh data for checking performance. That is why you split your data. There's two ways to do this, right? There's the way of saying, I promise to collect more data later, and that might just be a pain. Or you have one big data set now, so in advance, just split that thing so that you have some test data for later. That's like you're a professor. You have a bunch of calculus problems. You can either show them all to your students up front, but then you have to go invent 50 others for the final exam, or just save some, then use those for the final exam. Split your data. Now, we talked about overfitting, and you may be wondering, is there such a thing as underfitting? There is. Underfitting happens out of hubris. When you say something like, I learned about straight lines in school, and I insist on using a straight line to solve this problem. There you go. The straight line doesn't fit your data nicely, you didn't let your data speak, and so you get bad performance. Congratulations. It's much better to let your data speak. But be careful, when it starts to speak, it begins to overspeak very enthusiastically, and so there's going to be this balancing game where you're going to need to rein in that enthusiasm. That's why we have all those extra steps down the line. Now, in practice, underfitting is not the scary one, and you almost never hear about people fussing about it. And the simple reason for that is that you can diagnose it easily right in the data where you've done it. You fit your model, you got the performance score, it is obviously a bad performance. And so you don't even move to any next stage, and you don't even try to launch a system like this because it obviously sucks. Overfitting, on the other hand, is a silent killer. If you don't check it on new data, the performance in the data set that you use to build your stuff will look too good to be true. You won't know there's something wrong. If you connected all the dots, things will look perfect. And the only way you see that is if you test properly on new stuff. And if you're not very careful about testing properly on new stuff, you end up with systems that will bleed horribly. So you got to take this really seriously. This is the nightmare. What we're actually worried about, the monster, is bad performance, right? We want good performance. Make it work is what we're about. And the reason that overfitting is the one you hear about is that overfitting is the manner by which you end up with applied disasters of bad performance, because this one's easy to catch and that one's less easy. So, the way to overcome this is to be very careful about data splitting. And excuse me while I wax lyrical, sometimes my friends tease me that if I had to have 4 words written on my tombstone, they would be, split your damn data. I think this is pretty much the best idea in science, data science, and so forth. data splitting is the reason we can have machine learning. When you have no data, you have at best an opinion and there's no way to test the opinion. One data set, and you can either use it to form an opinion, but who knows if that opinion holds any water, or you can form an opinion in advance of the dataset carefully by meditating in a closet, and it's really hard and you have to use your imagination, but you can check if that opinion is nonsense. Two datasets, you can now use one of them to get inspired, and another one to check if your opinion is nonsense. But your second dataset has only one round of ammunition. It's a one-shot thing. So if you got inspired by some nonsense, yeah, you can find out that it was nonsense, but you go home empty-handed. So you're protected from going and spouting nonsense all over the place, but you don't get the thing you wanted. So then it makes you very careful about whom you trust to do the exploration and analytics, data mining stuff, to suggest the thing that's worth following up rigorously. And you sure aren't going to trust that to some dumb algorithm, are you? 3 datasets. Well, with a third dataset, you have a soft interim check, and now it doesn't matter who can have a go at getting inspired, because you can filter out all the clearly bad ones in the interim check. So now you can let, I don't know, you have a go, machine learning has a go, tea leaves have a go, what have you. And you can take all those opinions and you can check them on the next data set, and you can throw all the ones that are obviously not worth going for. Or if all of them suck, you can go back and iterate on this as many times as you want and then have your final one, final test at the end. And so it is 3 data sets that unlocks the whole thing, the whole ability to do machine learning properly. And today the modern way is 4 data sets. And we'll talk about what the 4th one is later. Most people still say 3. Humanity is evolving to 4, now that we have lots of data. Anyway, so let's split our damn data. So our original data set, we're going to split into 2 pieces, as I mentioned, for exploration and testing. Refining and designing solutions, and checking whether those solutions should or should not be built. Then, the exploratory data, we will split another 2 ways into a training piece and a validation piece. In-class examples, practice problems. This allows us to build models. This allows us to check how we're doing and have do-overs if we want to. So the reward for this is letting you tinker as much as you like. You don't even have to understand what you're doing. Just try stuff. Out come some recipes. Put them in here. If you don't like what's happening, go back there. Back and forth as many times as you like. And when you think you've got the one, moment of truth, test it and see if it actually is legit. And as a trained statistician, a lot of that, and undergrad and grad, by the way, so a lot of years in this mindset, the world of a statistician is very dark. We're so twitchy, we're so nervous, because we are dealing with those situations where there's no do-over, and then it really matters how we have said we think our universe works. We curate the assumptions. Very careful. With this stuff, all we're asking is, does it work? And so it actually doesn't even matter if the assumptions do or don't hold, if we know what they are, if we don't, if we check them. As far as building this stuff, run the data through it. Don't worry about what the underlying method is, because if it doesn't work, and if those assumptions were all screwy, you find out immediately, and then you go back and try something else. So you don't have to be anxious anymore. Be free, my friends. Realize just how freeing this is. You wanted to go and math through the assumptions? Why? Just have fun. Just tinker, dabble, play. It's a great time to be alive. Step 4. Look at some of the data. Are we going to look at all of our data? What do you think? Exactly. You have gotten the point of the previous stage. Which dataset will we look at? The training data only. Now, why might we do this? Partly because we might be spoiled for choice in terms of features. We have the option to put any of 3 billion ingredients in. Which combination of ingredients should we put into our cucumber salad? Well, if we don't know anything about these ingredients because they're all labeled with barcodes, It's like being in a dark warehouse full of ingredients, and one way to do it is grope around there at random and pick some up and put them into your microwave and hope for the best. Another way is to do analytics first on your training dataset, bring your flashlight, and have humans look around and think about what might be worth pursuing. Not for sure what's going to work, just what seems to be a fruitful endeavor. The domain expert plus the analyst together. Analytics pays off, as we saw. It helps you engineer good features. It helps you zoom in, narrow in to good solutions. Another reason we'll do this, say we're doing this wine picking thing, and we're working with the age of the wine. And that was calculated from data where we recorded the year. And we had a big wine tasting party, and our friends were there. They were also drinking, which affected how they were recording the data for us, which is great. And so we have this big spreadsheet with the years of the wine. And we could just pick that up and put that right into our model and never look at it. But we might also open up that training data, and then we notice that the computed age of the wine is sometimes reasonable, 2 years, 6 years, and sometimes it seems to suggest that the wine is from the Roman Republic. Now, maybe it is indeed Roman wine. Or maybe someone put in 2 digits where they should have put in 4 digits for the year of the wine. And we wouldn't realize that unless we put our eyeballs on the data and actually checked what might be going wrong with it. So this is a step where we are inspired to see if there is any smelly bug in there, and should we write a fix. And we will hopefully not clean that up by hand. We'll clean it up algorithmically, and we will apply the fix not just to the training dataset, but to all 3 datasets, because you want the world represented by all 3 datasets to be the same world. So you shouldn't only fix one and leave the other 2. Then you've got Roman Republic wine in your test dataset, and things will go wrong. So this exploration thing really helps. Feature engineering, cleaning things up. Selecting feature subsets. Step 5, getting the tools. So in this step, we're going to get hold of some algorithms, and we are going to apply them to our dataset. And as I mentioned earlier, the difference between all these named algorithms tends to boil down to what is the allowable shape of the final recipe. What sort of object are we going to use to try to separate our data? Are we going to try to use one line that can have any slope it wants? Or are we going to say, no, it has to be vertical and horizontal, but feel free to use multiple lines? Are we going to go for something super flexible? There are many more options beyond these. The math in machine learning, let me spell it out again, is in service of one of 2 things. Finding patterns in old data, or figuring out if new stuff works. Machine learning researchers care more about this one, and that's what's in the machine learning courses. How do you build a better microwave if you don't understand how this one works? Applied machine learning cares about this second one. This is the statistical math. This is not to be sniffed at. It's still something that you should take seriously, and it is math that you should master if you want to be part of the technical side of the application. So it's not like applying it means there's nothing, that no equations ever in your life. There should still be someone who's responsible for that careful, rigorous assessment, that statistical stuff, in your project. And that's what Applied will focus on. But before you get to testing it, though, from your applied perspective, what are we dealing with? We've got ingredients, then we are shoving through some algorithm, we get a recipe out on the other side, and of course we don't just serve that recipe immediately, we got to taste it, but the first recipe you try is never going to be the one that works properly, so in practice you're going to shove a whole lot of different ingredient combinations through a whole lot of different algorithms, and you're going to get a whole lot of results out, and then you will taste them all and see what's worth iterating on, just like in a kitchen. And this seems straightforward until you realize that your world is this. Oh my goodness. Okay, take a deep breath. First things first. Not all of these will be available to you in whatever framework programming language you have chosen, so it's already simpler. After that, you will aggressively eliminate bad options. So don't look for the perfect right option. Instead, take everything that's available to you and throw away the obviously bad ones. So some ways we do some throwing away. You know what label you want. It's a binary label, like yummy, not yummy. This method wants to output for me a multi-class label, like cat, dog, bear, giraffe. Clearly not a match made in heaven. Throw away that method. What about learning type? You want to do supervised learning? That method is for reinforcement learning. Okay, throw it away, it's not for you. How about dataset size? Can it actually handle the dataset that you're trying to deal with? If not, what are we even doing here? Available info. Your inputs have nothing to do with the timestamp. It rather insists it wants a timestamp, okay? Not for you either. And so you go through this list, and eventually that's what you're left with. It's aggressive elimination that you're going to do. And then of these, which are you going to try? Whichever you have time for. So then the trick, the applied machine learning engineer, they eventually do end up learning a lot about the nature of the algorithms just from practicing. They don't have to when they start out, but they end up learning this stuff kind of in the way that you learn the names of a cast of bad soap opera characters just by being in waiting rooms. Not because you're trying to, but mere exposure. So you learn this stuff in the end, but what you want to try to study up on purpose, is not how the algorithms work. It's how long does each one take to try on the various kind of data situations. If you have a good handle of that, you are an extremely potent, powerful machine learning engineer. And so if you know this one takes 2 seconds, this one takes 5 seconds, and this one takes 2 years, well, what order are you going to do it in? You'll only try the difficult one if the other ones don't give you any love. And so Google engineers, they keep coming to me because they spend too much time around researchers. We've got a huge research division here. They keep coming to me being like, Cassie, here's my problem. They tell me the problem. Which algorithm should I use? Should I use thing or should I use thing? And I have to remind them, okay, thing 1, how long does it take to try? 2 minutes. Thing 2, how long does it take to try? 3 minutes. Why are you here asking me? You should have tried them already. And even if the textbook says don't try it anyway if it takes no time. Because what the textbook is recommending is based on assumptions. Your business problem is not in the textbook, and you don't know whether those assumptions hold for your business problem. Hey, try it anyway, you never know. You find out by tasting it. So, in practice, if the inputs and outputs into an example that comes with that software package look kind of like your inputs and outputs, and it doesn't take that much fuss to re-wrangle your data set to shove it in there, go for it. See if it works. If it doesn't, try something else. Iterate towards a solution. That's what you're doing. Let go of anxiety. And so my advice is not to be the person who suffers most in machine learning, the perfectionist. Perfectionists have a really hard time here. They really are anxious about getting it right first time. You're never going to do that. Free yourself to make a glorious mess, because that's what it takes to succeed in the end. You never get it right first time. Okay, now it is time for lunch.